Greetings, ladies and gentlemen. My name is Ryan Shazani and welcome back to another physics video. In today's video, I'll be going through how to find the electric field at a point above an infinitely long wire. So let's take a look at this diagram. There's a point A, and below point A, L meters below it, is an infinitely long wire with a charge density of lambda. So how are we going to tackle this problem? There's actually two methods that I'm going to be going through in today's video. The first method is by utilizing Gauss's law, which is the closed surface integral of the electric field dot the closed surface is equals to the total charge over epsilon naught. This is Gauss's law, also known as one of Maxwell's four equations. So Maxwell equations, E&M, electrodynamics. So this is the first method by utilizing this equation. The second method is actually by the brute force method, or the longer way, which is just to integrate dE or integrate dQ over 4 pi epsilon naught r squared. So this is the longer method. I'll be going through the first method, which is by using Gauss's law, and then I'll be going through how to use the second method. Alright, let's start. So for us to use Gauss's law, we actually have to draw another diagram. So let's draw the same wire, the charge density of lambda. And for this diagram, we have to draw the Gaussian surface, or also known as a closed surface. Okay? And then we're going to find the electric field at point A, which is here, point A. And this is distance L away from the wire. Same thing as this. And we can also say that the height of this closed surface, or of this closed surface which looks like a cylinder, which is a cylinder, is capital H. Alright? Now, if you take a look at this Gaussian surface, it is made up of two kinds of surfaces. The first is the flat surface, and the second, this is the flat surfaces, and the second is the rounded or curved surface. So for us to actually use Gauss's law, we actually have to write two expressions. So first is the closed surface integral of the curved surface plus the closed surface integral of the flat surface. Is equals to the total charge enclosed in this Gaussian surface, which is just H times lambda over epsilon naught. Alright? Now, let's take a look. So if you realize, this is actually the expression for electric flux. Am I right? And if you take a look at the flat surface, the electric field is actually parallel to the flat surfaces. So since flat surface is parallel to the electric field, therefore the electric flux of the flat surface is equals to 0, i.e. is equals to 0, right? And also, because electric field is constant everywhere, or is constant everywhere at the edges of the curved surface, then I can also say that I can just convert this into a scalar a scalar quantity. Therefore, I can say that the total thing is just can move the E to the front, and dA, this is the curved, is equals to, or plus 0 is equals to h lambda over epsilon naught. Alright, now this is actually just the area, which is just the circumference times the height, and that is 2 pi L H equals to H lambda over epsilon naught, and therefore electric field is equals to, so the H, so lambda over 2 pi epsilon naught L, and voila, this is the electric field at point A. Now this is the first method, which is actually quite easy, but because we are utilizing Gauss's law. But now we're going to take a look at how we're going to be using the brute force method, or by using the continuous charge distribution method. Alright, so now we'll be going through how to use the continuous distribution method by utilizing the integral of dq over 4 pi epsilon naught r squared. Okay, so we'll be using this method. So to use this method, we actually have to make this diagram a bit more comprehensive. Let's take a look at just one point. Okay, so this point has a point charge dq, or an infinitely small charge dq. And what we're going to be doing is we're going to be finding the electric field due to a point charge at point A. So this distance would be distance x, and the distance between the point charge and the point A will be r, and I'll make this angle theta. So I'll do this for every single point in the wire, and then I'll add up, basically integrating dq over 4 pi epsilon naught r squared. Okay, so how are we going to do this? It's quite simple. First, we can substitute dq to be equals to lambda dx, because this tiny distance, or this infinitesimal distance, is actually just dx, right? And then we can just substitute this, and we also know that r squared is equals to x squared plus l squared, which is just Pythagoras theorem. So let's continue writing this. Lambda dx over 4 pi epsilon naught r squared, which is just x squared plus l squared. Okay, and then we're going to be integrating this from negative infinity, because with respect to dx, right? So negative infinity to infinity distance. But if you take a look at this, this is actually quite complicated. We don't really want to solve this, right? So how are we going to solve this? We actually have to simplify this even further. But before we simplify the algebraic terms even further, we can simplify this whole way of visualizing it even further. So because this is an infinitely long wire, at the other point of the wire, this point x, we can also see that there is also an electric field due to this point, and an electric field due to this point. And the horizontal components of both will cancel out, because let's say there's also distance x away. I.e., what I'm saying is we only have to consider the vertical direction of the electric field. The horizontal part will cancel out because of symmetry, right? So due to symmetry, they'll cancel out, and because of that, I'm going to add a cosine theta in front or behind. Why cosine theta? Because let's take a look at this. So if this is the wire, then this point A, and here, electric field looks like this, right? And this theta, we'll just be considering the vertical point. So we'll take just the total electric field times cosine theta. This is just to get this. Okay, understand? So apart from this, we can also substitute cosine theta to be in terms of something else. So cosine theta is equals to L over R. And you also know that x squared plus L squared is equals to R squared. So let's just continue substituting this. And dx is also a bit complicated because we don't want to integrate infinity, right, to infinity, which is just absurd. So what we can do is we can actually write tangent theta is equals to x over r. Therefore, x is equals to r tangent theta. Sorry, so r is L. And if you were to differentiate this, it will be dx is equals to L secant squared theta d theta. So let's substitute everything. Dx is equals to lambda L secant squared theta d theta over 4 pi epsilon naught x squared plus L squared times L over R. But if you take a look, R squared is equals to x squared plus L squared. So R is just basically equals to the square root of x squared plus L squared. And then we can change this to be from negative pi over 2 to pi over 2, because we are integrating it in terms of, or with respect to d theta. And if you take a look, angle, if the wire were to be an infinite distance, theta would be reaching infinity. Sorry, theta will be reaching pi over 2, and the other side will be reaching negative pi over 2. So if this is at infinity, and this angle is pi over 2. Okay, understand? So let's simplify this equation even further. So this is equals to over 4 pi epsilon naught x squared plus L squared 3 over 2. Okay, now let's try to substitute the x squared. Over 4 pi epsilon naught x squared is equals to L squared tangent squared theta plus L squared 3 over 2, right? And this will just be simplified to over 4 pi epsilon naught L squared plus one plus tangent squared theta. And 3 over 2. Okay, now take a look at this. 1 plus tangent squared theta is just secant squared theta, am I right? So let's simplify this even further. Okay, and then what are we going to do next? We're actually going to simplify this. So 3 over 2, so this is just integral of pi over 2 negative pi over 2 lambda d theta over 4 pi epsilon naught L secant theta. And secant theta here is just cosine theta, right? So let's just move the secant theta up. So cosine theta. And this is basically just equals to lambda over 4 pi epsilon naught L integrate from negative pi over 2 to pi over 2 of cosine theta d theta. And this will just give me lambda over 4 pi epsilon naught L sine theta negative pi over 2 to pi over 2, and it's just and voila. So therefore the electric field at point A is equals to lambda over 2 pi epsilon naught L, and it's the same answer that we get by using the Gauss's law method. So I hope this made sense, and I hope you enjoyed today's video. If you found this video helpful, then make sure to subscribe and like the video and share the video. And I'll see you in the next video. Thank you. Goodbye.